the binomial theorem. All right, the application of the binomial theorem says that if I would have, say, 1 plus 4 to the 6th power, let's make it x plus 4. So x plus 4 to the 6th power. If you want to do the binomial theorem, how did you guys do x plus 4 to the 6th power? How did you learn how to do that? Well, we could do lots. I could write x plus 4 times x plus 4 times x plus 4 times x plus 4 times x plus 4. But does anybody, well, I don't know if I counted 6 times. Probably not. As you go through that, we could do it the hard way and a whole lot of distribution and simplifying and compacting and blah, blah, blah. Or, anybody use Pascal's triangle? Right? Anybody heard of Pascal's triangle where it's just 1 and then 1, 1 and 1, 2, 1 and a 1, 3, 3, 1 and 1, 4, 6, 4, 1 and then a 1, 5, 10, 10, 5, 1 and then a 1, a 6, 15, 20, 15, 6, 1. That's a 6. So I'm going to pick that row. And this thing goes an x to the 6th, then a x to the 5th times 4, and then an x to the 4th times 4 squared times an x cubed times 4 cubed, x squared times 4 to the 4th, and a x to the 1, and then a 4 to the 5th, and finally a 4 to the 6th. And the coefficients are 1, 6, 15, 20, 15, 6, and 1. Right? You'd write down these coefficients, 1, 6, 15, 20, 15, 6, and 1. And then I notice that the powers go x to the 6th, x to the 5th, x to the 4th, x to the 3rd, x to the 2, x to the 1, x to the 0. Then I go 4 to the 0, right? There's a 4 to the 0 there. 4 to the 0, 4 to the 1, 4 to the 2, 4 to the 3, 4 to the 4, 4 to the 5, 4 to the 6. Anybody remember this? Anybody ever do that? Yay, raise your hands and say, we all know this. Kind of, sort of. All right. Where in the world did this come from? This is a counting problem. Can I ask, well, how is this a counting problem? Well, if I look at a problem, say, square plus triangle to the nth power. If I wanted to multiply it out, like you said, a bunch of distribution, this would be square plus triangle times square plus triangle times dot, 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 times square plus triangle. How many factors are here? There are n factors. We're going to do this n times. Plus means what in terms of counting? Or times means what in terms of counting? And. All right, let's look at it this way. What are you doing? I have n tables in front of me. On every table is a square with a triangle. And what do I tell you to do? Go by every table and take one thing from each. So what do? I take a square or a triangle and take a square or a triangle and take a square or a triangle, and I would go through this entire thing, right? So what happens is this right here simply says take a square or a triangle n times. That's all that is saying. So we go through this, I'm going to take a square or a triangle n times. Is everybody okay with that? But if you did do that, how many objects would you end up on the other side? I'd have n of them, right? If I actually did it, I would have n objects. Which are just simply, they'll have squares and triangles, right? We'll have I'll have n squares and triangles. Okay, I have n squares or triangles. All right, I could have, say, first off, I could have n squares and no triangles. Make sense? I could have all squares. I could have gone through and had all squares and no triangles. So that'd be first case. What's the second case? Well, I could have had one triangle, but that means how many squares did you have? N minus 1. Or I could have had two triangles, but then how many squares did I have? N minus 2. Or the nth version of this, I could have n triangles and have how many squares? 0. All right, is everybody okay with that? If you have n things that are two types, squares and triangles, you could have n squares, no triangles. Or you could have n minus 1 squares and one triangle. Or you could have n minus 2 squares and two triangles. Is everybody okay with that ordering? Okay. How many ways, how many of these are there? Well, I could do a count. I could do a choose function, right? How many total ways to arrange n objects are there? N factorial. How many of them are squares? N factorial. How many of them are triangles? 0 factorial, right? So if I would look at this, think about it this way. I have n blocks. How many arrangements of n blocks are there? N factorial, but a bunch of them are squares. You divide by the squares and you divide by the triangles. But what is that? That's n choose n or n choose 0, depending on who you want to talk about. If we focus on triangles, we'll say it's n choose 0. What's this guy? So this is equal to n choose 0 square to the n, triangle to the 0. But what's this? Well, there's n factorial arrangements, but there's n minus 1 factorial, but that is n choose 1, n minus 1, triangle to the 1. Or this is n choose 2, square to the n minus 2, triangle to the 2. What are each of these coefficients? Each of these coefficients are how many ways to arrange n objects, n factorial. How many of them are squares? Divide them out. How many of them are triangles? Divide them out so I can get rid of my overcount. And we keep going down through this process until we get n choose n, square to the n minus 2, triangle to the n. Each of these are the word or. If each of these are the word or, what am I going to do with every one of those? I'm going to add them. So you tell me you want to take n things out of two possible objects. How can you do that? Well, that would be the objects added to the nth power, but that's the same as n choose 0, square to the n, triangle to the 0, and this becomes the binomial theorem.
On that last one, n choose n,
Yep.
square to
Oh,
0.
that should be 0. So we get square plus triangle to the nth power is n choose 0, square to the n, triangle to the 0, plus n choose 1, square to the n minus 1, triangle to the 1, plus somewhere in here is an nj, and that's square triangle. We have j triangles, that means that n minus j squares, and then we keep on going until we finally get n choose n, square to the 0, triangle to the n. And that's the binomial theorem. Pascal's triangle isn't here yet. But this is just using choose functions. And so if I would do, for example, what is 3x minus 2y to the 4th power? How do you do this? We just simply do this and say, ignore your coefficients for a second. This is 3x to the fourth, negative 2y to the 0. We will have a 3x to the third, negative 2y to the first, 3x to the second, negative 2y to the second. We'll have a 3x to the 1, minus 2y to the third, and then a 3x to the 0, and a negative 2y to the fourth. Notice how the powers of one go down, the other go up. And what are all the coefficients? 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. That's a direct application of the binomial theorem. The binomial theorem has plus, so the sign of the middle is actually attached to the second object. Then what do I have to do? I have to simplify this entire thing down. 4 choose 0 ends up being 1. 3 to the fourth, x to the fourth, negative 2y to the 0 will make this thing 81x to the fourth. And so I'd have to simplify all of this work. All the choose functions. For example, what is 4 choose 2? It's 4 factorial divided by 2 factorial, 2 factorial. We have to simplify it. Equals do the algebra. I'll let everybody do that at home for fun. Because it's awesome. We all like factorials. All right, so we can put in anything we want as long as we follow this pattern. It allows us to do some kind of interesting things. Say, for example, what would be 1 plus 1 to the nth power? Seems kind of silly. That's just simply 2 to the nth, right? But what's the binomial theorem say? By the binomial theorem, this is the square and this is the triangle, right? So that tells me that this is 1 to the n, 1 to the 0, 1 to the n minus 1, 1 to the 1, 1 to the n minus 2, 1 to the 2, and we keep on going till we get 1 to the 0, 1 to the n, and this is n choose 0, this is n choose 1, this is n choose 2, and this is n choose n. What's 1 to any power? 1. So what happens to all those 1s? They're 1s. So what's left? How many of you does this seem obvious? 2 to the nth is n choose 0 or n choose 1 or n choose 2 or n choose n. So you're saying that I have n objects, I could choose none of them, or I could choose one of them, or I could choose 2, or blah, 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 choose n. That's the same thing as 2 to the nth power. It doesn't seem obvious, but we've actually used this. You have a set of n objects. You pick none of them. What subset do you have? The empty set. You have a set of n objects. You choose one of them. What sets have you formed? The singletons. You have n objects. You choose 2 of them. What have you formed? The duals. So what is this actually saying? What this is saying is if you have n objects, that is every subset you could ever make. Choose none to choose all. What was our formula for the guy who collected all the subsets. That is the what? The power set. What is the cardinality of the power set? Anybody remember that? It's 2 to the number of elements that you have. This is just the cardinality of the power set. It ends up being it just shows up again. It's just a counting problem if we want to think about it that way. You either have it or you don't. What's like, what do you have? It's like, we'll go through it. It's 2 to the nth. Well, how could I do it? Choose none, choose 1, choose 2, choose 3. Every one of these chooses would tell you how many subsets you would have to look for the guys that have 1, or the guys who have 2, or the guys who have 3. So you have to make them out. Using this formula here occurs a lot. We just got to put whatever we want into the squares and the triangles. Like in the book, they plug a 1 and a 1. They plug a 1 and a -1. They plug in a 1 and a 2. Right? And then they use the formula and simplify it out. If I plug a 1 and a -1, that's 0. And 0 to the nth is 0. So 0 is equal to what? Choose 0 minus choose 1 plus choose 2 minus choose 3 plus choose 4 minus choose 5. Well, if I took all the 1s to one side, the minuses to the other side, it tells me that the odd subset choices, sum, are the same number as the even subset choices. That's all that ends up being as we go through these. Using the binomial theorem will be things like, you should be able to take anything here at all. I should be able to do a 4x minus a 1/3 x to the 15th power all raised to the 121st power. And you should be able to maybe write the whole thing, or I could ask you, what would be the 17th thing in that expansion? And you could say, all right, on the 17th, find the pattern and pull the 17th out. You should be able to use the formula, which is right powers go down, right powers go up, write the choice in the appropriate order, and then simplify. So we should be able to use this formula. And since we had the SPTEs, I can't do, so after break, we'll talk a little bit about why Pascal's triangle is called Pascal's triangle. It ends up being that every row of Pascal is just the choice functions. And that tells me the sums of the Pascal's triangle. And actually, that formula we just did, what happens if you add each of these rows? I get 1, 2, 4, 8, 16. It's all powers of 2. Why? That right there. 2 to the nth is the selection of the rows. So every row of Pascal's triangle is just simply subset counters. But if I add them all up, it's 2 to the nth. It's kind of fun. You can play around with Pascal's triangle. Write it as a triangle where everybody's oriented on the left, and then look on the diagonals, and you find all the Fibonacci numbers. So there's lots of stuff you can find in this little triangle. All right, have a good break.